Section 13.2 is line integrals. So what we'll be considering is a function of two variables, f of x, y, and then some plane curve parameterized by t, where x equals x of t and y equals y of t, for t ranging between some two values in an interval. Now, what we could also do this in 3 dimensions, and we'll see that towards the end of the section. But for now, we'll just think of it in terms of plane curve C. What we'd like to do is integrate a function, f of x, y, along this curve C, which is parameterized by x of t and y of t. We can rewrite x of t and y of t in its vector form. Take note of that. We'll use that off and on throughout this section. And we'll assume that C is a smooth curve, which would mean that r prime is continuous and r prime of t is not 0. Now, in the interest of integrating a function over such a curve, what we'll do is we'll divide the interval AB up into subintervals ti minus 1 to ti. And that's seen down below. We don't have it listed in terms of t's, but we can see that, well, for each ti, we have an x sub I and a y sub I. The endpoints of each of these subintervals, subarcs is what we'll call these now. So here's a subarc along this curve. And so each one of these points along this is representing where a t sub I is, or an x sub I, y sub I. Now, that breaks us up into smaller arcs. If we find the function's value along one of these subarcs, x sub I star, y sub I star, then we can multiply the function's value, f of xi star to yi star, times the length of that arc, delta si is representing the length of the arc. And that'll give us roughly the integral of the function f of xy along that subarc containing the point xi star, yi star. Now, if we do that for all of these subarcs and sum them up from I equals 1 to n, then we'll get an approximation of the function's value along this curve, or the function's integral above this curve. Again, then, if we take the limit as n goes to infinity and shrink these subarcs to be infinitesimally small and have infinitely many of them, then we'll actually obtain the integral defined on the next page. And so we see here, we limit the max of our subarcs, so we shrink our subarcs to have a length of 0, and we obtain this integral, which is read as the integral along the curve C of f of xy ds, where ds is the infinitesimal arc length. We'll see what to do about that in a moment. So this is also called a line integral of f over c, or along c. Okay. Now, how to handle ds? This is the arc length in these cases. So it turns out that ds is actually parameterized by the following. So dx dt squared plus dy dt squared, square root of all of that. That's from our arc length integral from Calc 2 for a parameterized function in x and y of t. And if we plug that in for ds within our integral, we can argue that this is, the correct formula for this, but the details of that mathematically are a bit tedious. We end up with this formula here. So note that the right half of this, from the radical to the right to dt, is ds. Actually, so this is all ds written into the integral. It's just been swapped by that. So that is our integral of f along c, the line integral of f along c. And just another picture of what this actually looks like potentially. If we have a positive function, f of xy, or if it's positive at least above the curve c in the plane, then we'll have something that looks like the following in terms of a line integral. So remember that c is flat. C is this curve sitting in the plane on the page. Now f of xy is above that curve, on the above the plane essentially. If it's positive, it's above it in all places, never crosses it and goes under it. So what f actually is some curve in 3 space above this xy plane, and the line integral is actually the area underneath this curve, and it's been indicated by these columns all along it. It's the area of essentially this curtain or this wall that follows the curve C and has height f. So really what this is it's kind of like a single variable integral. It's just no longer along a straight line. It's no longer from A to B. It's along a curve C. And that's the interpretation of it if it's positive. If it's negative, then f would just cross underneath that curve at certain points, right? It might be underneath, running along it as follows in blue here. Maybe it crosses back up to intersect the red curve as well. So, but if it's just positive, we can think of it as the area of the curtain or the sheet that goes from the curve C in the plane up to the function f of x, y. So to see an example, we're asked to evaluate the line integral along C of x y to the 4th ds, where C is the right half of the circle x squared plus y squared equals 16. So our first parameterization is just direct. This is what things will look like typically if we don't convert to another coordinate system. I do this one just to indicate how the workflow might typically go. So if we're parameterized by this circle, we need to express y and x in terms of a single variable. It can be themselves. To not confuse things, we'll express it in terms of t. So we're going to let y be equal to t. And if we let t range from -4 to 4, well, then we'll go from a y value of -4 to 4. And if we're trying to include the right half of this circle, then y needs to range from -4 up to +4 for that right semicircle in the plane. And x needs to take on the values just positive square root 16 minus t squared. It's just the positive square root because we only want the right half of the circle or the right semicircle of this circle. Now, putting this together with the integral formula from the previous page, our line integral, as written here, now becomes -4 to 4, letting t vary along the interval that we've chosen for it, that we've as indicated for it. And then we have 16 minus t squared. This is x times y to the 4th, so t to the 4th, times the square root of the derivative of this x function squared with respect to t squared. Same thing for y with respect to t squared. And about here is when I would stop and say this is just too messy. But typically this is what things will look like, only the details won't be so messy. We won't have such obnoxious functions in these integrands and problems that don't need to be done in another coordinate axis. But you know, this is just to see how to translate directly from rectangular coordinates into this parametric function of t. So instead of doing that, I realized that I'm dealing with a circle, so it's much better off to use the second parameterization, which I describe a circle with radius 4 and the right half of the plane between -pi/2 to pi/2 for theta. So that's that right semicircle in the plane. Now x is 4 cosine theta, y to the 4th is 4 to the 4th sine to the 4th theta. So we can plug all these into our integral, and let's see how this goes from here. Our line integral becomes, we're going to let theta range from -pi/2 to pi/2. Replace x with 4 cosine theta. This is 4 to the 4th sine to the 4th theta. And then this is the derivative of x, which is the derivative of this function, all squared. And then plus the derivative of y. Remember, y is equal to sine theta. It's not explicitly written anywhere, but that's where this came from. Y equals sine theta, so that 4 sine theta, so this is 4 cosine theta is its derivative with respect to t. And that quantity is squared, and we take the square root of the whole thing, dt. And all of this from the radical to the right is ds, this portion of our line integral. And we've got everything set up, and we work from here. This radical simplifies to the square root of 16, which is 4. These constants multiplied to 1024, so they're out front. and we're left with sine to the fourth cosine theta, sine to the fourth theta cosine theta d theta. This is a nice u substitution. U equals sine theta, du equals cosine theta d theta. The integral of that is 1/5 sine to the fifth theta, evaluated from negative pi over 2 to pi over 2, maintaining what our constant multiples are up front. And the result of this is 8,192 over 5. So this is our line integral over the right half over the right semicircle in the plane with radius 4. So we can extend this idea not only smooth curves C, but to also piecewise smooth curves. So here's a sketch of what's going on in that situation. So we see C as a smooth curve, and then it connects to another curve C2. But at that point of connection, there's a cusp. Remember that points and cusps are points of non-differentiability. They're points of non-smoothness. You can literally see it in the graph. This is not smooth here. So what we'd have to do is split up the integral, this line integral. We'd do all of C1, and then we'd write another integral for C2 to split at any point of non-smoothness. And we see between C2 and C3, we have something similar, the same for C4, and we can do this finitely many times, up to C sub n. Now, the thing that must be the case is that it should at least still be continuous. Each of these smooth curves need to have a common initial point and terminal point from one to the next, as we see sketched below. Of course, we're assuming that there are a handful of curves between C4 and Cn, all which do actually connect until we count up to C sub n. Now, with that in mind, we'll use it in the problem below. But we also have another situation to consider, and that's just two other line integrals. They can be taken with respect to x or with respect to y. So instead of arc length, we can use distance along an x-axis or distance along a y-axis. These are just specific line integrals that might be useful for one purpose or another. So the line integrals of f along c with respect to the x and y-axis are this one with respect to the x-axis, this one with respect to the y-axis. Now dx is literally written in terms of t here. X prime of t is dx over dt. So we replace dx with x prime of t, dt. So that's the formula if we want to integrate with respect along c with respect to only x. Now we'll see a shorthand for that written below, and that's in this example. They ask us to evaluate the line integral along c of the integral x plus 2y dx plus x squared dy. So things have been split to components. We have a dx component, we have a dy component. So what we're actually being asked to do with this integral, what this integral is trying to calculate, is this is the line integral of the function along the x-axis as the x variable changes, and similarly, this is as the y variable changes, or along the y-axis for the curve c. We won't really look at a specific purpose of that, but noting that these are around will be useful to us. Sometimes the real purpose is just because the curve might simplify to just dx or to just dy, change along an x-axis or change along a y-axis. But at any rate, this shorthand means split this into two integrals, one with respect to x, one with respect to y. So they tell us that C consists of the line segments from 0, 0 to 2, 1 and from 2, 1 to 3, 0. Now these two line segments are two different smooth curves. They do have a terminal point and then an initial point in common, so they're still continuous, so they would more or less match up with what we've drawn on the previous page or talked about. But what we're required to do is split over each of these two curves. So we have C1 is the line segment from 0, 0 to 2, 1. And we'll recall a very useful formula. We'll need this throughout the section. If we're going to travel from the point AB to the point CD, and we need to construct the line segment that does so, it's 1 minus t times the first point plus t times the second point. 1 minus t times the initial point plus t times the terminal point. And we let t range from 0 to 1. This formula will always work to construct a line segment from one point to the next. We see that when t is 0, this is 1 times AB, so we're at the point AB, and this is 0. So we start at the point AB with t equals 0. When t is 1, this is 0, and 1 times CD leaves us at the point CD. So it does in fact work. We'll use this to create R1, the parameterization of the curve C1 with respect to the parameter t. And ultimately we get R1 of t is equal to 2t comma t. This is just combining components after multiplying through by the scalars 1 minus t and t. And then R2 is the curve from 2, 1 to 3, 0, and or the parameterization of C2. And after we plug in 2, 1 for its first point, 3, 0 for its terminal point, and collect like terms within each component, we have the following for R2. So we have parameterizations for each of our curves, for each of our line segments. Now we look at the integral itself. We realize that we have dx and dy, so we're going to integrate with respect to dx with x and then with respect to y. So we want to split that when we get to it. But first things first, we'll split over C1 and C2. And in both cases, t ranges from 0 to 1 to get from one point to the next. So our limits of integration will actually match thanks to us using the same formula. So 0 to 1 and 0 to 1 for each of these integrals limits of integration. That's C1 and then C2 left to right. Okay. And now let's match the parts in this integral. X plus 2y for our curve C1. So we're working with R1 of t along C1. So x is 2t, so there's x here, plus 2 times y, and 2 times y. Y is t, so there's 2 times t. And then times 2, where does that 2 come from? That's dx dt, or x prime of t dt. So this is the derivative of the x component. That's x prime of t, and then dt. Similarly, for x squared, this is x is 2t, because we're still along the curve C1. We square that quantity times the derivative of y, because dy dt is y prime of t dt. This is y prime of t dt. So we get that component. This is all using the formulas at the top of the page here. X prime of t, y prime of t dt for each. And we move over to C2 and we do something very similar. We have x plus 2y. This is x plus 2 times y. This is y. 1 minus t is y in the R2 curve. And then times the derivative of x with respect to t. So to point that out, this dx becomes dx dt, derivative of this function with respect to t, times dt, or x prime of t dt, and that's 1 times dt. Okay, similarly for y, or for the y integral, we have x squared, which is 2 plus t squared, and then times negative 1. Well, this is dy. dy is y prime, the derivative with respect to t of this function, which is negative 1 times dt. So we filled in all the parts. This is all according to the formulas at the top of the page here. So once we've got this written down, we're pretty happy about it. This function is entirely in terms of t in each integrand. And we can combine them if we like. It really won't matter since the limits of integration are the same. The variable of integration is the same. That won't usually be the case, but in this case it could be. We've kept them separate just so because that's the general procedure anyway. Find antiderivatives with respect to t of each of these functions. They're all polynomials, so it's very easy to calculate. Apply the limits of integration, and we arrive at an answer of 15 over 6. So that's our integral along a piecewise smooth curve, and with respect to x and y in a mixed integrand like this. So line integrals in space. So this generalization, we'll sort of gloss over this. Anything we could do in most of the things we do in R2, we'll also do in R3. Now we have the added z equals z of t. T still ranges from A to B. And we'll imagine, splitting up a subarc or an arc in three-dimensional space in terms of subarcs with lengths delta si. Along each subarc is a point xi star, yi star, zi star. And then we'd sum up all of those function values at each of these points within each subarc times the length of the subarc. And that would give us the approximation of, if f was a positive function, the area beneath the curve f and above the curve C in three-dimensional space. Of course, that's a four-dimensional situation, so it's a little bit difficult to imagine what that looks like. Now we take the limit as the max length of each arc, subarc approaches 0, and that, of course, gives us with this, leaves us with this line integral of f along the three-dimensional curve C. So it looks very similar to what we did before. Our line integral then breaks into the following: f at the point x of t, y of t, z of t, and then times the arc length term, this radical of all three derivatives squared with respect to t dt. So that's ds in the three-dimensional space. Should be no surprise, it's analogous to the two-dimensional space. Now, a more compact notation for this, or possibly even for the two-dimensional space, is to write things as f of vector function r of t times the magnitude of r prime of t dt. And let's see why that's the case. Well, r of t is x of t, y of t, z of t. So that takes care of that. And then r prime of t's magnitude is literally the derivative of x squared plus derivative of y squared plus derivative of z squared, all underneath the radical. So that is our nice compact notation for this situation, this term right here. So we'll see this off and on throughout this chapter and the next, or this section and the next. So continuing, we're asked to evaluate a line integral y sine of z, where c is the circular helix given by x equals cosine t, y equals sine of t, z equals t, and t ranges from 0 to 2 pi. This is nice. We're already given the parameterization, the vector function r of t, basically. We've compactly written it right here in vector notation, and we can get to work from there. In the previous example, we had points that line segments were attached to. We had to actually come up with the equation of those line segments. So this one's quite a bit easier. We have r of t written down, so we'll find the derivative with respect to t of r of t, and that's off to the right here, taking the derivative of each component, and then we'll find the magnitude of that to fill in the entire integral, and we'll have the square root of these the component derivatives squared, added together, sine squared plus cosine squared, both functions of t, is equal to root 2, or is equal to 1 plus 1 under the radical is root 2. So when we set this up, our line integral over the curve c of this function y sine of z is equal to 0 to 2 pi, as indicated here, and then y is equal to sine of t, so there's sine of t, and then sine of z is t, so this is the sine of t. Sine of z is sine of t in this case, times, and this is our magnitude of r prime of t function, or term in this case, dt. And that's just root 2 times dt. Now, of course, this root 2 won't always work out to be a constant. It might sometimes be a function of t, but in this case, it's a simple constant. So we would factor square root of 2 out of the radical, or out of the integrand, and we integrate from 0 to 2 sine squared of t dt. This is 1/2 t minus 1/4 sine of 2t from 0 to 2 pi. Evaluating it at those limits of integration, we have root 2 times, this comes out to pi, everything else is 0. And we have pi times square root of 2. So just as a little reminder, where this came from, to fill in some details here potentially, this formula is, this is our f of x, y, and z function, or in other words, f of r, and this is times the magnitude r prime of t, and then dt. Of course, this f of x, y, z can be written as r of t if we wanted to. I was just indicating what's what in that integral. Okay, so that's a three-dimensional line integral. So for a space curve, C, and let's see, line integrals of vector fields. Now we can consider a line integral taking place in a vector field. So these functions f have been somewhat component oriented, but now we can look at it directly as a vector function. So if f is a continuous vector field defined on a smooth curve given by the vector function r of t, and t ranges between a and b, then the line integral of f along c is the vector function f dotted with dr. And that's actually equal to f of rt dotted with r prime of t dt. Remember that r prime of t is dr dt. So this is now a dot product of two vector functions, f of rt dotted with r prime of t. Now this is also, interestingly enough, equal to f dotted with the unit tangent vector t ds. Okay, and this is because, just to make a little connection between these two, remember that the unit tangent vector t is equal to r prime over the magnitude of r prime and the magnitude of r prime, well, that's solving for this vector r prime, that's t unit tangent vector times r prime here, and that's really, this is not a proof or a derivation, but it's just sort of a little trick to see that this is more or less the case. R prime of t is essentially ds, right? So, or ds, r prime of t dt is unit tangent vector times r magnitude r prime times unit tangent vector ds. But more or less we see where this is coming from, or at least have a little bit of a link to it. So to use the formula, it's pretty straightforward. We just have a dot product in our integral for two vector functions, and we're asked to find the work done by the force field f of xy equals x squared I minus xyj in moving a particle along the quarter circle r of t equals cosine t I plus sine t j. T ranges between 0 and pi over 2. So from 0 to pi over 2, that is in fact a quarter circle for this function. And that's for the parameterization given here. Now x will be cosine t and y will be sine of t based on each of these assignments from our parameterization. And we'll plug those into this. This is our other vector function. So f dotted with dr, integrating over this curve c, it will be exactly the work. Remember, force times the distance is equal to work. So in this integral, we've got the force of the vector field, the force field dotted with r prime of t dt. So this is r prime of t dt, derivative of the x component with respect to t, derivative of the y component with respect to t. dt, and this is actually a little bit easier than any of the other ones we did. It's just a straightforward dot product, and once we complete that dot product, we have -2 cosine squared t sine of t dt. This is a u substitution. U equals cosine t, so du is negative sine of t dt. That integrates to 2/3 cosine cubed t from 0 to pi, and evaluating at the limits of integration, we've got -2/3. So that puts together a work calculation with a force field F over a function R of t, or over a curve R of t. Now our last example is a center of mass example, and for all of these we'll suppose that we have a wire in the shape of a smooth curve C, just to match our line integral notion of this smooth curve C. As linear density function rho of xy. To find its mass, it's the same formula we've always used, only now it's a line integral. We integrate the mass, or we integrate the density function over the length C, and we get the mass. To find the center of mass, x bar, y bar, the x component for the center of mass is 1 over m times the integral of x rho of xy ds. Remember, x rho of xy is the moment, the first moment of x. And similarly for y bar, we'll have a y rho of xy, line integral there as well. And the example we're looking at is a wire takes the shape of a semicircle, x squared plus y squared equals 36, with x greater than or equal to 0. So here we've drawn something like it on the right half of this plane. X is greater than or equal to 0 with a radius of 6. It's thicker near its base, or its ends, than near the top of the arc. So down closer to the y-axis, it's thicker. At the top, it's thinner. And it has to find its center of mass and its mass if the linear density at any point is proportional to its distance from the line x equals 6. So here's the line x equals 6. It's a vertical line. And our density is proportional to the distance from the line x equals 6, or from the value of 6. This is an expression of that. So the further we are from x equals 6 on this circle, the larger the density. Right? So when x is 0, when we're here along the y-axis, we're at the densest, we should be at the densest portion of this. And in fact, we are, right? That's 6 times k, versus when x equals 6, we're at the very end here, and x equals 6 gives us 0 times k, which is a density of 0, which doesn't really make sense for a wire, but we're going to let it go. We can still do the mathematics involved. To parameterize the curve, we have r theta, where r is 6. We're directly on this curve, and theta ranges from -pi/2 to +pi/2. And then x is 6 cosine theta, y is 6 sine of theta. And to find the mass, well, the original integral would look like this: the density function, line integral over c. And we quickly realized that we'd probably rather than deal with the limits of integration that would be complicated for what x is equal to as a function of y, we convert to these polar coordinates that we've suggested. We integrate from -pi/2 to pi/2, that right semicircle. And then k times 6 minus x is 6 minus 6 cosine theta. And then ds, this is x prime of t squared plus y prime of t squared, or theta squared in both these cases, square root of all that d theta. So all of this, just to make a little note of it, is ds in this problem. It's the arc length calculation that we'll need. And with a sine squared plus cosine squared term underneath that radical, we get a 1. 6 squared is 36. So this is really the square root of 36. And what we see below is that there's a factor of 6 right here. We factored another factor of 6 and k to the front of the integral. Add this, and we're ready to move along. It's a fairly straightforward integral of 1 minus cosine theta. We get theta minus sine theta, evaluate from -pi/2 to pi/2. And we get 36k pi minus 2 for our mass. So we'll use the mass and the formula for the centers of mass, because we need 1 over m for each of these. And moving down to that, we see for our first calculation, x bar, the center of mass, the x coordinate for the center of mass. We have 1 over m as declared. And then we have the integral from negative pi over 2 to pi over 2, x, which is 6 cosine theta, times rho of xy, which is k of 6 minus x, which is 6 minus 6 cosine theta. And then we have the square root of, it's our ds term. Once again, it's the same as it was in the integral above. So I've shortened it. 6 squared times each of these functions of theta is 36 times sine squared plus cosine squared theta. That's a 1 for the trig identity. And we have square root of 36 d theta. Comes out as a 6. We factored another constant of 6, and our 2 factors of 6's factored out to give us a 36, and k has been factored out to the front of the integral as well. And both that 36k in the numerator cancels with the 36k in the denominator. This 6 that remains is factored out as well to be 6 over pi minus 2. And the integral of this integrand, cosine theta minus cosine squared theta, well, the first part is just sine theta, and then minus the integral of cosine squared theta, and that's given in parentheses here, negative 1/2 theta plus 1/4 sine 2 theta, and then evaluate from negative pi over 2 to positive pi over 2. And simplifying the details of this, we get 12 minus 3 pi over pi minus 2. That's our value for x bar. Now, y bar, we can guess before we even calculate it, is, since this is symmetric in terms of the x-axis, then we know that y is going to be equal to 0. We're right along this y, or this x-axis for our center of mass coordinate for y. What I suggest the student to do, or the viewer to do, is to prove that this is the case by actually calculating y bar using the formula similar to the x bar formula. And you'll see that when you're done with all the details of that you get 0. And that's a nice check. You can use a lot of the things that are similar to what we've done here. And it's a nice practice to get started on some of these integrals. So overall, our center of mass is this x coordinate, comma 0. So one thing to do, an astute student would look back and say, okay, is 12 minus 3 pi over pi minus 2 somewhere between 0 and 6? And if you use a calculator or some other means of estimation, you'll find that that actually is the case. So that's it. That's our line integrals. We've ended on all up to centers of mass of wires that follow the shapes of curve C. And we've seen force fields and just general line integrals for the sake of line integrals. We'll do more with line integrals in section 13.3, where we see a fundamental theorem for line integrals.